Hello, my name is Dr. C. Suresh Kumar, working as a lecturer in mathematics at TR Government Degree College, Kandukur, Prakasam district. In this session, we learn about basic properties of vector subspaces. First of all, we learn about what is a vector subspace. Let Vf be a vector space and W be a non-empty subset of V. Vf is a vector space, that is V is a vector space over the field F, and W be a non-empty subset of V. That is, all the elements of V are belongs to V. Then W is said to be a vector subspace of V if W itself a vector space with respect to the operations, same operations defined on V. They are vector addition and scalar multiplication. W is a subspace of V, then W plus is a subgroup V. That is, W plus is a group. W plus is a group. Since V subset of V, V is also a subspace of V, and the zero vector, the set with the zero vector is also a subset of V. Hence, zero vector set is also a subspace of V. These two subspaces, V and the set with zero vector, are called improper or trivial subspace of V, and the remaining, except these two, the remaining subspace are called proper or non-trivial subspace of V. Next, we'll learn a theorem, that is, namely, this theorem belongs to the necessary and sufficient condition for a set W to be a subspace of V. The conditions are alpha minus beta belongs to W and A alpha belongs to W. Proof. Assume that W is a subspace of V. Then W is a vector space itself under the operations defined on V, and also W is a subgroup of V plus. If alpha beta belongs to W, then alpha minus beta belongs to W. This is our first condition. And for the second condition, since W is a subspace, hence W is a vector space, and hence from the definition of vector space properties, W plus is an abelian group and W is closed with respect to scalar multiplication. So for every A comma belongs to F and alpha belongs to W, we have A alpha belongs to W. These two conditions we have to be proved. And the sufficient condition, assume that W be a non-empty subset of V and satisfying the given two conditions, and we have to prove W plus W is a subspace, that is, W is a vector space itself. For that, we have to prove the properties of vector space, that is, One is vector addition and 2 is a scalar multiplication, and the third one is vector addition and scalar multiplication, both the properties involved. And one identity law. In Roman letter 1, we had to prove W plus is an abelian group. For that, there are 5 laws involved in abelian group. They are identity law, inverse law, closure law, associative law, and commutative law. And the first one is identity law. From these conditions, by the given conditions used, we had to prove identity law. Alpha and alpha belongs to W. By the first condition, alpha minus alpha belongs to W, that is 0 bar belongs to W. So 0 bar is the identity element, 0 vector is the identity element in W. And the second law, inverse law, that is for each element in W, there exists its inverse element in W. If we take 0 bar belongs to W and alpha belongs to W, from the first condition, 0 bar minus alpha belongs to W implies minus alpha belongs to W. So minus alpha is the additive inverse of alpha. Next, closure law, that is alpha comma beta belongs to W, alpha comma, if we take alpha beta belongs to W, from the inverse law, minus beta is also in W. From the first condition, alpha minus beta belongs to W. From this, alpha plus beta belongs to W. Alpha plus beta belongs to W. Next law, associative law. Since W is subset of V, that is all the elements of W are the elements of V, hence W is associative with respect to vector addition. Similarly, commutative law also holds since W is subset of V. From these 5 laws, we tell about W plus is an abelian group. W plus is an abelian group. And second property, we had to prove W is closed under scalar multiplication, that is from the given condition 2, A belongs to alpha, alpha belongs to W, F A alpha belongs to W, that is scalar multiplication property. And third property, since W is subset of V, all the elements of W are the elements of V, we had to prove the 4 properties, namely A into alpha plus beta equal to A alpha plus A beta, A plus B into alpha equal to A alpha B alpha, A into B alpha equal to AB into alpha, and 1 into alpha equal to alpha. From these 3 main properties, W itself a vector space under the operations of V, that is W is a vector subspace. This is the important theorem described about vector subspace. And another theorem, this is also a necessary sufficient condition for a non-empty subset W of V to be a subspace, is A alpha A comma B belongs to F and alpha beta belongs to W implies A alpha plus B beta belongs to W. For the proof, let W be a non-empty subset of Vf, and necessary condition, assume that W is a subspace of V. Then W is a vector space with respect to the operations defined on V. If A comma B belongs to F, alpha beta belongs to W, then by scalar multiplication property, A alpha belongs to W. Similarly, B belongs to F and alpha beta, B beta belongs to W, then B beta belongs to W. From closure property, A alpha plus B beta belongs to W. Since W is a vector space, so we prove the required condition. Then assume that the sufficient condition, assume that the condition holds, that is AB belongs to F and A alpha plus B beta belongs to W. Now we have to prove that W is a subspace, that is W is a vector space, and now we have to verify the three main properties of vector space. The first one is closure law. 1 belongs to F, alpha beta belongs to W. By using only condition, we have to prove W is a vector space. From Roman letter 1, we have to prove W plus is an abelian group. For that, the closure property is 1 belongs to F and alpha beta belongs to W. So in the given condition, 1 into alpha plus 1 into beta belongs to W, that is alpha plus beta belongs to W. This is closure law. And the second one is associative law. Since W is subset of V, hence we get the associative property, alpha plus beta plus gamma equal to alpha plus beta plus gamma. And the third law, identity law. If we take 0, 0 belongs to F, alpha beta belongs to W, then 0 into alpha plus 0 into beta belongs to W, that is 0 bar plus 0 bar belongs to W, that is 0 bar belongs to W. This is called the 0 vector as identity element in W. And fourth property, inverse law, that is each element in W has additive inverse. For that, if we take -1 and 0 belongs to F and alpha beta belongs to W, then by using the given condition, -1 into alpha plus 0 into beta belongs to W, that is minus alpha plus 0 bar belongs to W, so minus alpha belongs to W. Minus alpha belongs to W. This is identity law, inverse law. And fifth one is commutative law. And commutative law easily holds because since W is subset of V, we get if alpha beta belongs to W, then alpha plus beta equal to beta plus alpha. From these 5 properties, we call W plus is an abelian group. W plus is an abelian group. And the second property, that is scalar multiplication property. If we take A comma 0 belongs to F and alpha beta belongs to W, by the given condition A alpha plus 0 beta belongs to W. That is A alpha belongs to W since 0 beta equal to 0 bar. So this is scalar multiplication property. And the third one is the third property holds because W is subset of V. We get all the elements of W or the elements of V. We have to prove easily by A into alpha plus beta equal to A alpha plus A beta. A plus B into alpha equal to A alpha plus B alpha. A into B alpha equal to AB into alpha. And 1 belongs to F and alpha belongs to W implies 1 alpha equal to alpha. From these three properties, we have W is a vector space, hence W is a subspace of V. These two theorems are very important role in vector subspaces. These two are the necessary and sufficient condition for a subspace. Thank you, one and all.